We've seen the structure of matrix A in terms of a transformation of A. Actually, we didn't even have to use the idea of a transformation except when we mentioned the column space. And we see that V equals Rn consists of a row space of A, a null space of A, and that any vector in A is a unique sum of a vector in the row space, a vector in the null space. Of course, we also know that the row space is orthogonal to the null space. Now, we define the transformation, which we did mention previously, but didn't really define. The transformation will take any vector V in Rn, and it will map it over to Rm. So let's call this space here W equals Rm, so that V goes somewhere over here in W. And we'll call this this image T of V. And of course, T of V is defined to just be the product of the matrix A with the vector V. Now, all the vectors in the null space map onto the zero vector over here in Rm. And all the vectors in the row space map somewhere else in Rm. Now there are vectors in Rm, or there might be vectors, usually are vectors in Rm, that are not the image of any vector from V. Okay, so this subspace maps onto space over here that includes the zero vector, because of course the zero vector is in both the row space and the null space. It's the intersection, so the zero vector over here would actually be right here at the intersection of the row space and the null space. But all the vectors here map into this subspace, which we're going to call the column space. So this is the column space. All the vectors in the null space, every vector in the null space, maps onto the zero vector, because of course that's what we mean by a null space. Now recall that any vector V up here is a sum of a unique vector that I'll call V row and a vector V sub n, V row in the row space, V sub n in the null space. So V equals V row plus Vn. And that's unique, so I'm going to put an exclamation point over the equal sign. Not necessarily standard notation, but exclamation point generally indicates something, not that's surprising, but something that's unique. Unique in that for any vector V here, V row, there's only one such V row here, and only one such Vn here that add up to this vector. So, again, there are infinitely many, assuming that n of A has dimension greater than or equal to 1, there are infinitely many vectors here that will add up to different vectors in Rn, none of them in this or this. But all the vectors that you get by adding members of the null space to this one map to the same vector over here. So that if I have another vector, call it U equal VP plus, now I'm running out of notation. I wanted to call this U sub n. I'm going to call this Vn prime. So there's another Vn prime over here. Just any other vector, some other vector in the null space. Any vector in the null space other than this one is going to give you a vector U here. And let's designate that by this. Well, if this unique decomposition of the U vector into a vector from the row space and a vector from the null space involves the same vector from the row space as this one, then it's easy to prove that this vector also goes here. Okay, the only other thing I want to say about this is that this column space is the row space of A transpose. And I said this in the preceding video. Simply, if you transpose a vector, you switch the rows and the columns. Well, it follows that the row space of the matrix is equal to the column space of the transpose, since the rows of one are the columns of the other, and vice versa. So this is very easy to see. Okay, now we're working toward applying this entire picture to determine the best fit line to data. Now that's not our only goal. Our secondary goal, or actually our primary goal, is to understand the structure of these spaces and how they work, and at least this one profound application of this entire idea. So we will continue with developing that idea.